Waves and electromagnetic radiation. In this video, we're going to be defining transverse and longitudinal waves. We'll define electromagnetic radiation, and in the process talk about wavelength, frequency, and amplitude. We'll identify the relationship between all of these values, focusing on wavelength and frequency, and doing a calculation from wavelength to frequency or frequency to wavelength. And then we'll introduce the basics of wave interference, talking about the difference between constructive and destructive interference. There are two types of waves, as well as some blended versions that we aren't going to be discussing here. A transverse wave includes things like light waves, or if you were to pluck a guitar string, while longitudinal waves include sound and pressure waves. We're going to be spending all of our time in this chapter on transverse waves. Electromagnetic radiation is a large part of our daily lives. For this chapter, we just need to define it a bit better and talk about some specific properties. Some examples in our daily lives include things like heat, or microwaves, sunlight, or X-rays. Can you think of some other things that might be considered electromagnetic radiation? Other examples that you may have thought of are radio waves, AM or FM, gamma rays from space, cell phone signals, garage door openers, remote controls, and a variety of other things like that. Now let's talk about some specific things that you're going to need to be able to identify in order to calculate EM radiation. We can talk about amplitude here, although we won't be doing a lot of calculations with it for electromagnetic radiation. But amplitude is just half of the distance from the peak of the crest to the bottom of the trough, or the highest point to the lowest point. Things that we will be working with continually, though, are wavelength and frequency. Wavelength is the distance that it takes to go one full rotation through a wave. Here it's shown from this point to the other point as shown on the picture. Frequency might be a bit tougher to picture. It's the amount of cycles that the wave has in 1 second. I find students have an easier time visualizing it with spinning. So stand up for a second and spin around once in a circle. Now do this a few times. If it took you 1 second to do one cycle, then you're going to be doing 1 cycle per second. We call that a hertz. Now, let's say that maybe you were a bit faster and you were doing 2 spins for every 1 second. Now you'd be spinning at 2 hertz. The same works when looking at this in a wave. If it goes from one point on the wave through a full cycle to the next point in 1 second, it has a frequency of 1 hertz. If it goes from one point on a wave and it goes through 2 full cycles in 1 second, that would be 2 hertz, and so on and so forth. Given that we know the speed of light, we're able to convert between wavelength and frequency. Something to be a bit careful about here is what the nu looks like. It looks awfully close to a V, and in fact in many fonts looks identical. You'll need to pay attention to this sort of issue when you're reading problems to make sure that you know whether you're dealing with nu or whether you're dealing with velocity. Electromagnetic waves are actually made of 2 components, an electrical and a magnetic component, that have the same properties, such as wavelength and frequency, but they're perpendicular to each other. As with all electromagnetic radiation, they travel at the speed of light. Wavelength and frequency, which we will soon see also determine energy, is what decides the properties of the waves. This is what distinguishes the different types of electromagnetic radiation that we talked about at the beginning of these podcasts and in other podcasts. Let's look at how energy, frequency, and wavelength are related. If wavelength increases, what happens to frequency? Since light travels at the same speed, if we're going to increase the wavelength, then the frequency must decrease. Now let's answer a few more questions. Take a moment and pause in between each one before I give the answer if you need to, so that you can try to work on it on your own first. So first off, between the red and the blue light, which has the greater frequency? So you can do this in a few different ways. You can look at the graph and you can see where each of the blue light is. You can relate it to the wavelength and then convert that into frequency, or you can just trace up and look at the frequency. So in this case, our blue light is going to have the greater frequency. Now let's go ahead and look at which has the greater energy. So if you look at both again, doing the same sort of issue where you can look at the wavelength or you can follow it up and look at the energy, you can see that blue also has the higher energy. And here we have a relationship now between frequency and energy. That as frequency increases, so does energy. One more. Now, does blue light have a greater speed than red light? We've said that it has a higher frequency and higher energy. So how does that relate to its speed? And no, most certainly not. It's all light, and so it's all going to have the same speed, and that's c, or the speed of light. Now, let's do one example where we interchange between frequency and wavelength. We'll practice some good problem-solving techniques along the way, so we'll write out all of the things that we know that relate to this problem and what we want to know. Given that we have an equation that converts between the known and the unknown quantity, we know that we can fill in all of our known quantities into the equation we have. So I'm going to write these out for you, and then you should take a moment, pause, and try to solve the problem yourself. Since c is in meters and wavelength is in nanometers, we're going to need to make sure that we convert to the same unit. Hopefully you remembered to do this, but if you forgot, now you'll know for the exam. I'm going to convert the nanometers into meters. I think that generally this is the easiest way to go about it. Hopefully you know your metric conversions, but if not, take a moment and go back and review those. We'll convert from the 522 nanometers, dividing by 10 to the 9th nanometers, to get 5.22 times 10 to the negative 7th meters. From here, we can fill into our equation. We have nu is equal to c over lambda, so we can fill in our c, or our speed of light, and we can fill in our wavelength, now properly converted into the right unit. Finally, you should check your answer and make sure that you have the right number of sig figs and the right units. Notice here I went ahead and converted to hertz. You could also write it in 1/seconds if you followed the units from the previous part, but either way would be okay. Just make sure that you know that if I write it in hertz, that it's also equal to 1/seconds if you need to use that for something. I'd like to end this section now with a way to help you remember the visible region, at least when it's of a higher energy, or at least which is of a higher energy. I don't expect you to memorize the table of the electromagnetic radiations, and I wouldn't expect you to be able to replicate that for me. But in the visible region, it's really useful to have a basic idea of which one is the higher and lower energy. So here I have a comic for you. And he walks in and he asks if the counter has a blue bowl. And the counter guy says no. And he slowly goes through all of the colors, working his way all the way down to red. And finally, the guy at the counter says, yes, here's a red bowl, and gives him the red bowl. And he says to his friend, oh, I was hoping for something a little higher energy. This seems a little silly, but it can help you remember that actually blue violet end of the spectrum is of the higher energy than the red side of the spectrum. And hopefully the little comic helps you remember that part of it. Now let's move on to talk about wave interference. Waves will interfere with each other if they come into contact. Now, a great way of being able to picture this is thinking about what happens when you drop two pebbles in a pond. The ripples are going to come in contact with each other, making new patterns that are very different from the simple circles that they started with. The same thing will happen with light waves. Now let's look at this interaction, or more correctly phrased, look at this interference a bit more closely. Think back to your early math days when you had to add two waves together. You may remember having to go through point by point and add them up to show what the new wave looked like. So let's do this first with the top figure. If we start here, and if we start at the beginning, and we add these 2 points together, you'll see that the amplitude is still going to be 0. As you move to the next, let's say the peak, and if we were to arbitrarily put those each at 1, when we add them together, they're not going to equal 2. So it's going to have increased. And we could do this point by point by point until we get the wave that's on the right-hand side of the constructive image. This gives us a wave that's larger than the two waves that we started with. This is called constructive interference. Now, in destructive interference, the waves are overlapping in a way that cancel each other out to some degree. It doesn't have to be complete, which we'll talk about in a minute. So if we look at the second part of this figure, where I have it labeled destructive, we can see that at the peak of one wave, it lines up with the valley of the other. And so the peak and the valley will cancel. At the zeros, they'll cancel as well because it's 0 and 0 to still equal 0, and everything cancels out to 0. This would be called complete destructive interference. Again, it doesn't have to be complete, but in this case it is. Now let's look at this one. So take a second before I start talking and look at it. You may want to pause. This is a little different from the last one. The top wave that we're adding to the bottom wave is now double the size. So it's destructive interference because overall the waves are canceling out. But it isn't complete destructive interference because the bottom wave is only half the size of the top wave. And so at the end, we still get a wave. However, that wave is smaller than the initial one. Now, in all of these, for simplicity's sake, I've been using waves that are in what we call the same phase, so the peaks and the troughs kind of line up, or an exact opposite phase, so that the peak and the trough lines up. This doesn't have to happen either. These can be much more complex and create a variety of different patterns, but we're not going to go through and do the math for that because it's just not particularly necessary for this chapter. So hopefully now you know a bit more about electromagnetic radiation. You understand that it has two components that are perpendicular to each other. And most importantly, you understand about wavelength and frequency and how those are interchanged and used with energy. We'll talk a little bit more about energy to frequency to wavelength conversions in later podcasts. We also know that the waves can interact with each other and that this can be done in both a constructive and a destructive manner. And we'll learn more about all of these conversion factors in the next videos.